What's going on, everybody? All right, this is meteorologist Zachary Clark, just bringing you lecture number 2. I am going to upload lecture number 1 on here on YouTube as well, and onto Facebook. Just trying to get a YouTube channel started as well, just to provide some basic information on meteorology. There'll be a little bit of physics in here as well, if you guys are interested. This is just something I've been passionate about for a long time. Also, the intro music here was provided by Guitars and Ghosts. That is a YouTube channel. I definitely will be linking that channel in the description here as well. But thank you guys for viewing this. Definitely appreciate you taking the time out just to learn a little bit about meteorology. So, like I said, it's been a passion of mine since I was 3 years old. The movie Twister is what got me into meteorology, actually. So definitely, all right, let's get this started, guys. All right. So let's talk about the Earth-Sun geometry for a little bit. So the Earth has an elliptical orbit around the Sun. So this basically means that the Earth's orbit is not a perfect circle. Rather, it is slightly oval-shaped. This means that there is a point in Earth's orbit where it is closest to the Sun, and another point where the Earth is farthest from the Sun. And the average Earth-Sun distance is about 93 million miles. And then there's two terms to be familiar with. So the first one is aphelion, which is the furthest Earth-Sun distance, which occurs in early July. So we're approaching that coming up here. It is June 20th right now, so right in early July, right around July 5th, is when we are the furthest distance away from the Sun, actually. And it is about 152 million kilometers away from the Sun at this point, or 94 million miles. We're looking right here. So here's the Sun here right in the middle. Over here is where we're going to be around July 4th, July 5th. The next one is perihelion, which is the closest Earth-Sun distance, which occurs in early January. So that would be all the way on here, the left-hand side, at 147 million kilometers, or about 91 million miles. So the difference between aphelion and perihelion is small compared to the overall distance between the Earth and the Sun. So there's about 3 million mile difference there between 94 million miles and 91 million miles. And this actually is not the cause of the seasons. We'll definitely get into that a little bit later here in this lecture. All right, let's talk a little bit about declination and the Sun angle. Let's actually start with the Sun angle first. So the angle the Sun's rays make with the surface of the Earth is called the Sun angle. The Sun angle also changes throughout the day. So the Sun angle is 0 degrees at sunrise as well as sunset. The Sun angle is maximum at local noon. The Sun angle is negative at night since the Sun is below the horizon at that point. To find the Sun angle at noon, we need to know the Sun's declination angle and our latitude. And then we use the formula. The Sun angle is equal to 90 degrees plus the declination minus the latitude. So if the formula gives you a Sun angle greater than 90 degrees, subtract your answer from 180 degrees. So if this formula gives you 130 degrees, then the Sun angle at your location would be 180 degrees minus 130 degrees, which is 50 degrees. Let's talk a little bit about this picture here. Sorry, guys. So toward the poles, sunlight strikes the Earth at a shallow angle and is spread over a larger area so that the energy is diffused. So it's spread out. Right here in the middle, at and near the equator, sunlight strikes Earth at a steep angle, delivering more heat and light per unit area. And down at the bottom, toward the poles, South Pole in this case, more sunlight also is reflected by the atmosphere and Earth's surface when it strikes at a shallow angle. So it's basically the same in the South and North Pole. You get a more shallow angle. At the equator, though, we get more sunlight and a steeper angle. Let's take a look at declination here, guys. So, let me go back 1 second. So in this case, when sunlight shines at the Earth at a lower angle, closer to the horizon, the energy of the sunlight is spread over a larger area, and therefore is weaker than if the sun is higher overhead, and that the energy is concentrated over a smaller area. A sunbeam approximately 1 mile wide falling on the ground from directly overhead versus a sunbeam impacting the ground at the angle of 30 degrees. Trigonometry tells us that the sine of 30 degrees is 1/2, whereas the sine of 90 degrees is 1. Therefore, the sunbeam hitting the ground from an angle of 30 degrees spreads the same amount of light over twice as much area. Consequently, the amount of light falling on each square mile is only half as much. In the third case, showing the angle of the sunlight striking the Earth in the northern and southern hemisphere, when Earth's northern axis is tilted away from the sun, when it is winter in the northern and summer in the south. Basically, that explains the declination angle there, guys. So that is described by the Greek letter delta. All right, let's get into the seasons here. So the seasons occur because the Earth's axis is tilted by 23.5 degrees with respect to the plane of its orbit. This means that the declination is not constant, but changes over the course of 1 year, from plus 23.5 degrees to minus 23.5 degrees and back. The change in maximum sun angle over the course of the year is what results in the temperature difference between the seasons. This is because the lower sun angle means less energy per unit area in the sunbeams. The lower sun angle means sun rays travel through more atmosphere and lose more energy before striking the surface. Changes in maximum sun angle changes the length of the days as well as the nights. The equinoxes occur when the declination is 0. The sun is directly over the equator at that point. The solstices occur when the sun is at maximum declination, either north or south, of 23.5 degrees. And then the astronomical seasons and climatological seasons are actually different. Let's take a look at that. So astronomical seasons are defined from the solstices and equinoxes. So the winter solstice to spring equinox is from December 21st through March 21st. The spring equinox to summer solstice is from March 21st to June 21st. And then the summer solstice to fall equinox is from June 21st to September 21st. And the fall equinox to winter solstice is September 21st through December 21st. Now, climatological seasons are actually defined from experience. So winter occurs December, January, and February. Spring occurs March, April, and May. The summer is from June, July, and August. And autumn is from September, October, and November. All right. So let's take a look at energy, heat, and temperature. Let's first start off with energy. Energy is defined as the ability to do work. And work is the creation of motion in the presence of an opposing force. There's a few types of energy. So we have kinetic energy, which is the energy of motion, defined as work needed to accelerate a body of given mass from rest to its stated velocity. And we also have potential energy, which is stored energy, defined as energy held by an object because of its position relative to other objects, stresses within itself, its electrical charge, or other factors. And also, kinetic energy is the energy of an object has because of its motion. It depends on the object's mass and velocity. Potential energy is the energy that results from the position or shape of an object. Take a look at thermal energy, guys. It is defined as the total kinetic energy of all the atoms and molecules that make up a substance. It refers to several distinct physical concepts such as internal energy of a system, heat, or sensible heat, which is heat exchange, in which the exchange of heat changes the temperature of the body or system as well. It also changes some macroscopic variables of the body or system while unchanging other macroscopic variables such as pressure or volume. You can see here the image here. You can see the molecules moving pretty quickly. So we're definitely going to take a look at this on how this actually affects temperature. Let's take a look at temperature. So temperature is a measure of the average of kinetic energy of all the atoms or molecules of a substance. Adding heat to a substance raises its temperature, and subtracting heat will lower its temperature. And temperature is actually not energy. There are a few methods of energy transfer we'll take a look at, the first of which is conduction, a process by which heat energy is transmitted through collisions between neighboring atoms or molecules. This occurs more rapidly in solids and liquids where particles are closer together. Think of a frying pan set over a stove. The heat from the oven, whether powered by gas or electric, causes the molecules in the pan to vibrate faster, thus making it hotter. These vibrating molecules collide with their neighboring molecules, making them also vibrate faster. As these molecules collide, thermal energy is transferred via conduction to the rest of the pan. If you have ever touched the metal handle of a hot pan without a pot holder, you would have experienced firsthand the conduction of heat. And since air is a poor conductor, most energy transfer through conduction occurs right near the surface. And then this actually occurs in the atmosphere as well. Conduction directly affects the temperature only a few centimeters, a foot or so, into the atmosphere. So during the day, sunlight heats the ground, which in turn heats the air directly above it via conduction. At night, the ground cools, and the heat flows from the warmer air directly above to the cool air to the ground via conduction. On clear sunny days with little or no wind, the air temperature can be much higher right near the ground. Although sunlight warms the surface, heat flow from the surface to the air above is limited by the poor conductivity of air. A series of thermometers mounted at different heights above the ground would certainly reveal that air temperature rapidly falls off with height. All right, let's take a look at the next process. This is known as convection. Convection is defined as the transfer of heat energy in a fluid. This type of heat is most commonly observed in your kitchen when you boil water. That's what happens in the atmosphere there, but let's take a look at this. So air in the atmosphere indeed also acts as a fluid, much like water does in a pot when you boil it in your kitchen. The sun's radiation strikes the ground, thus warming the surface. As the surface temperature rises due to conduction, take a look at that right here. Heat energy will be released into the atmosphere, forming a bubble of air which is warmer than the surrounding air. This bubble of air rises into the atmosphere. As it rises, the bubble cools with the heat contained in the bubble moving into the atmosphere. You can also think of this bubble of hot air rising. The air is replaced by the surrounding cooler, more dense air, which is what we feel as wind. These movements of air bubbles can form small air masses observed as cumulus clouds. So I'm sure you guys have seen cumulus clouds like this. They basically look like, you can say, cotton balls. Some people say popcorn. But definitely, right on the screen here is definitely a nice example of cumulus clouds. And meteorologists refer, let's see. Well, actually, let's take a look at these cumulus clouds again. So it is these movements that are responsible for many weather pattern changes observed all across the world. Meteorologists refer to horizontal convection as advection. Advection is the transfer of an atmospheric property from one location to another. Let's take a look at radiation. Radiation is defined as the flow of electromagnetic energy between the sun and Earth's surface as it is influenced by aerosols, clouds, and gases within the atmosphere. It includes both solar radiation, or sunlight, and long-wave radiation, thermal, and several factors influence the amount of solar radiation from reaching the Earth's surface and the amount of radiation leaving Earth's surface. So basically, like I just reiterate, solar radiation is electromagnetic radiation, which is very interesting. So the factors that influence the amount of solar radiation from reaching the surface and the amount of radiation leaving Earth's surface include cloud droplets, humidity, temperature, atmospheric gases, aerosols, and the characteristics of the land and ocean surfaces. And all objects actually emit radiation. You can see here. So this is the campfire. It actually it releases radiation in the form of heat. You can also say, just moving on to more advanced topics of radiation, radiation is comprised of electromagnetic waves, or EM waves, of differing wavelengths. Shorter wavelengths, or higher frequencies, are more energetic. Visible light comprises only a small portion of the electromagnetic spectrum. Ultraviolet radiation has shorter wavelengths than visible light, and infrared radiation has longer wavelengths than visible light. The electromagnetic spectrum is divided into shortwave and longwave radiation, with the dividing line at about 4 microns. So, laws of radiation, just to reiterate, all objects emit radiation, even an ice cube. No object can be colder than minus 273 degrees Celsius, which is absolute zero. Let's take a look at the Stefan-Boltzmann law. So, hotter objects radiate more energy per unit area than cold objects. With this fact, we can determine that the sun radiates 160,000 times more energy than the Earth. In fact, we only receive 0.5 billionth of a percent of the sun's total energy. This, however, is enough to power the entirety of New York City for about 2 days, collecting light for 12 hours in an area the size of a football field. So, Stefan-Boltzmann law basically states that the total energy radiated per second is the luminosity, which is L, which is equal to 4 pi r squared times sigma times the temperature to the 4th power. Each square meter of the star's surface emits sigma t to the 4th watts. And a spherical star of radius r has a surface area of S equals 4 pi r squared. So a star's luminosity is related to both star size and temperature. Hotter stars emit more, larger stars emit more. Let's take a look at the next law here, guys. It's known as Wien's displacement law. So Wien's displacement law states that the hotter the object, the shorter the wavelength of maximum radiation. If we plug in temperatures of the Earth and the Sun, we will see that the maximum wavelength is about 10 microns for the Earth and about 0.49 microns for the Sun. Whereas the Earth emits mostly infrared radiation, the Sun emits mostly visible light. In fact, 43% is visible, 37% is infrared, and only about 7% is ultraviolet. Wien's displacement law also allows us to determine temperature of other stars depending on its color. Most of the time, something like that glows. Most of the time, something that glows blue is much hotter or much warmer than something that glows red. Objects that are good absorbers of radiation are also good emitters. So basically, a perfect absorber and emitter of radiation is called a black body. Take a look at that here in a second. So a black body is defined as a hypothetical body consisting of a sufficient number of molecules absorbing and emitting electromagnetic radiation in all parts of the electromagnetic spectrum, so that all incident radiation is completely absorbed and in all wavelength bands and in all directions isotropically. Maximum emission is realized. The Earth and the Sun are nearly black bodies and are often assumed to be for simplicity. So the two best examples of black body radiation are the Sun and hot stove, also the Earth, both of which emit red light due to their temperatures. When heated, the molecules comprising a perfect black body vibrate and emit light in the same wavelength as their vibration. Even the fictitious planet of Mustafar from Star Wars emits black body radiation due to its immense quantity of lava. So just to reiterate, black body radiator, all incident radiation is absorbed, and emitted radiation is only a function of the radiator's temperature. All right, guys, so let's take a look at solar radiation. So the sun emits at about 6,000 Kelvin, while the Earth emits at 288 Kelvin. From Wien's displacement law, the sun emits its peak radiation at a wavelength of 0.46 microns, which is in the visible part of the electromagnetic spectrum, which is actually green light. The Earth emits its peak radiation at a wavelength of 10 microns, which is in the infrared portion of the electromagnetic spectrum. So just take a look at that here, guys. So the sun is between 5,800 Kelvin and 6,000 Kelvin. And the Earth is between 250 Kelvin up to 288 Kelvin. So, from the Stefan Boltzmann law, the sun emits 7.35 times 10 to the 7th watts per meter squared of energy per unit area. The Earth emits 390 watts per meter squared of energy per unit area, which is a difference of 189,000 times as much energy from the sun than the Earth. Incoming solar radiation can be absorbed, reflected, or scattered by the atmosphere or Earth's surface. All right, so let's take a look at absorption. Absorption is a process by which the incident or incoming radiation is retained by a substance. In the case of the atmosphere, when it absorbs energy, the result is an irreversible transformation of radiation into another form of energy. This energy is transformed according to the nature of the medium doing the absorbing. The absorbing medium will only absorb a portion of the total energy, leaving the rest of it to be refracted, or scattered. The energy absorbed can also be transmitted back into other portions of the atmosphere. The atmosphere, due to many different gases and particles contained therein, absorbs and transmits many different wavelengths of EM radiation. The wavelengths that pass through the atmosphere unabsorbed constitute a phenomenon known as an atmospheric window. Atmospheric windows show lines of transmission through the atmosphere. The valleys of the windows are the windows where very little attenuation of the radiation occurs by the medium as it passes through. An absorption is mainly caused by three different atmospheric gases. Popular to contrary belief, water vapor causes the most absorption, not carbon dioxide. Carbon dioxide is number 2, and ozone is number 3. Atmospheric radiation helps our planet in two ways. First, absorption helps people by preventing high energy radiation from reaching the surface, which limits our exposure to harmful radiation. Secondly, it helps us by acting as a source of heat. If one were to take a vertical cross-section of the entire atmosphere, one would note that the temperature gradually increases with height. This temperature increase is caused by an increase in absorption of EM radiation with height due to the higher concentrations of higher energy wavelengths absorbing gases present at higher atmospheric levels. 20% of EM radiation is absorbed directly in the atmosphere primarily by ozone in the stratosphere, oxygen and nitrogen in the thermosphere, and water vapor and clouds in the troposphere. 50% of electromagnetic radiation is absorbed by land masses and oceans. All right, let's take a look at reflection. Reflection is a process by which a surface of discontinuity turns back a portion of incident radiation into the medium through which the radiation approached. Reflection is important to take into account since about 1/3 of the energy from the sun is reflected. If it were not for reflection, there would be a large portion of the world around us that we would not see. If an object does not emit its own light, it has to reflect to be observed. To have true reflection, the real discontinuity in the index of reflection is required. This discontinuity must be significant compared to the wavelength of radiation, or the energy could not be returned by way of refraction rather than reflection. An example of this would be a stratified cloud deck where more refraction occurs than reflection. 30% of EM radiation is reflected back into space by both clouds and the surface. And reflection has almost everything to do with albedo, which albedo is defined as the fraction of radiation reflected by a surface. The albedo of Earth is around 0.3, so albedo ranges from 0 to 1. Let's take a look at scattering. Scattering is defined as the redirection of EM energy by suspended particles in the atmosphere. This the type and amount of scattering that occurs depends on the size of the particles and wavelength of the energy. There are three main types of scattering that impact incoming solar radiation. The first is known as Rayleigh scattering. Rayleigh scattering occurs when radiation or light interacts with molecules and particles in the atmosphere that are smaller in diameter than the wavelength of the incoming solar radiation. Shorter wavelengths are more readily scattered than longer wavelengths. Light at shorter wavelengths, such as blue and violet visible light, are scattered by small particles that include nitrogen dioxide and oxygen. Since blue light exists in the shorter wavelength side of the EM spectrum, it is more strongly scattered in the atmosphere than the longer red wavelengths. Rayleigh scattering is actually responsible for the blue color of the sky. It can also produce haze in images, and at sunrise and sunset, the incoming solar radiation travels a longer distance or longer path length through the atmosphere. The longer path length leads to the scattering of short or blue wavelengths that is so complete that we only observe the longer wavelengths of light, the orange and the red. In the absence of particles and scattering, the sky would appear black, as the background of outer space. Take a look at the next type, right here on the right here, which is known as Me scattering. Me scattering occurs when the wavelength of the EM radiation is smaller in size or similar in size to the atmospheric particles. Me scattering generally influences radiation from the near ultraviolet through the mid-infrared portions of the spectrum. Me scattering mostly occurs in the lower portions of the atmosphere where larger particles are more abundant, and dominates when cloud conditions are overcast or mostly cloudy. Pollen, dust, smog are the major cause of Me scattering, and also produces a general haze in images. We also have a phenomenon called non-selective scattering. Non-selective scattering occurs when the diameter of the particle in the atmosphere are much larger than the wavelength of radiation. This is primarily caused by water droplets in the atmosphere. Non-selective scattering scatters all radiation evenly throughout the visible and infrared portions of the spectrum, hence the term non-selective. In the visible wavelengths, light is scattered evenly, hence fog and clouds appear white. Since clouds scatter all wavelengths of light, this means clouds block most of energy from reaching the Earth's surface. This can make interpreting and analyzing remote sensing imagery difficult in areas prone to cloud cover and fog. Clouds also cast shadows that change the illumination and relative reflectance of surface features, and this can be a major limitation in remote sensing imagery. And in remote sensing, it is important to understand the impact of atmospheric has on the electromagnetic radiation. First, it is crucial to understand atmospheric windows and to be able to identify whether or not a sensor can see through the atmosphere in a given portion of the spectrum. Because the atmosphere absorbs and scatters the incoming radiation, we often want to correct for these images. And the process is known as atmospheric correction. Let's take a look at that. And it's commonly used in image processing technique. So you can see on the right, this is the atmospheric correction here, guys. On the left, you can see this is where the image is not corrected. So it's definitely, you can see the big difference here. You can see more of the area here on the right. It's kind of blurry on the left. You kind of see that haze starting to build in there. But on the right, it seems pretty clear. Seems like a pretty clear image. And then just for fun, guys, real quick, let's take a look at the Martian sunset. It's definitely an interesting picture here, guys, from the Martian rover. So the atmosphere on Mars is different than that of Earth's and has a significant amount of fine particulate in the atmosphere. This causes different light scattering than what we observe here on Earth. The dust in the Martian atmosphere allows blue light to penetrate the atmosphere more efficiently than longer wavelength light. This causes the blue colors in the mixed light coming from the sun to stay closer to outer space compared to the wider scattering of yellows and reds. The effect is most pronounced near sunset, when the light from the sun passes through a longer path in the atmosphere than it does midday. This produces a blue-tinted sunset on Mars instead of the red and yellowish and orangish sunsets we see here on Earth. So just to recap, guys, scattering produces a bunch of weaker rays that move off in different directions. Scattering from small molecules is dependent on wavelength, which short wavelengths scatter more than shorter wavelengths. This is why the sky is blue and sunsets are orangish red. Scattering of larger particles is not wavelength dependent. This is the reason why clouds are white and also why hazy days appear white in color. Well, let's take a look at terrestrial radiation. This is defined as the portion of natural background radiation that is emitted by naturally occurring radioactive materials such as uranium, thorium, and radon within the Earth. As we know, the Earth emits infrared radiation. To balance the incoming solar radiation, the Earth must radiate at a temperature of about 255 Kelvin. However, the surface of the Earth averages around 288 Kelvin. Why is this, you wonder? Well, this occurs because of the greenhouse effect. The greenhouse effect is defined as the trapping of the sun's warmth, solar radiation, in the lower atmosphere, due to greater transparency of the atmosphere to visible radiation from the sun than to infrared radiation emitted at the surface. Greenhouse gases include water vapor. Have you ever noticed that the humid nights are warmer than dry, clear nights, or that deserts can be very cold at night? Now, this is due to water vapor. Also, carbon dioxide, nitrous oxide, methane, ozone, and clouds have a dual role in radiation balance of Earth. They reflect incoming solar radiation, keeping daytime temperatures lower, and they also absorb outgoing terrestrial radiation, keeping nighttime temperatures higher. So, when you have a cloudy day during the daytime, you'll notice that the temperatures are a little bit lower. Instead of being sometimes, say if it's 84 degrees, but then you get a big cloud deck that forms, temperatures may only reach about 79, 80 degrees. And also, when you have a cloudy night, these clouds absorb outgoing terrestrial radiation, keeping nighttime temperatures a little bit higher. So if the forecast low on a clear night is about 50 degrees, all of a sudden clouds start to form, and you get a nice overcast sky. Temperatures might stay up into the upper 50s, even 60s. There's definitely an interesting effect. So basically, to reiterate, some solar radiation is reflected by the Earth in the atmosphere. Most radiation is absorbed by the Earth's surface, which warms it. Some of the infrared radiation passes through the atmosphere. Some is absorbed and re-emitted in all directions by greenhouse gas molecules. The effect of this is to warm the Earth's surface and the lower atmosphere. And the last topic with just to briefly mention, because in the next lecture I'm definitely going to talk a little bit more about this topic, but that is known as latitudinal heat balance. So the tropics have a net surplus of heat, and the polar regions have a net deficit of heat. Mid-latitude regions are the battle zone. So right here in the United States, right in the mid-latitudes here. So just from, I'd say, Oklahoma all the way up through all the way up through North Dakota, South Dakota. And then heat must be transported from the tropics to the poles. And latitudinal heat balance is what drives the circulations of the atmosphere and the oceans. So latitudinal heat balance is actually what drives our weather systems here and the sun. So you could say the sun definitely drives our weather systems here on Earth, according to the latitudinal heat balance aspect. So we have a deficit at the South Pole and a deficit at the North Pole and a surplus near the equator. So this must balance out. So we have, this is why storms develop down in the tropics and go up towards the northern hemisphere, like hurricanes, typhoons, cyclones, things like that. And the same thing happens in the South Pole. So it's definitely an interesting topic. The next lecture will all be directly dedicated to temperature. So it'll definitely be an interesting lecture. I hope you guys enjoyed this one. I know I'm not very good at teaching, but I figured I'd just try my hand at it. You know, and always got to try it just to get it out there, you know? All right, guys, I definitely appreciate it. Hopefully, you'll join me for the next lectures. Never stop chasing.